Okay, gang, on to Chapter 7. In Chapter 7, we're going to look at building construction. And as you guys probably figured out, we're just taking a brief look at a whole bunch of different areas in this text. And reason being, we're trying to give you a good overview of all the classes you're going to cover in your degree classes. So let's look at our objectives for this chapter. Describe the 5 categories of construction recognized by the National Fire Protection Association. Explain how each construction category reacts under fire conditions. Identify the various construction elements of each category. Describe the potential hazards that each construction possesses to firefighters, and identify the various forces and loads that affect building integrity, and explain how these forces and loads can cause building failure under fire conditions. Identify construction elements that may contribute to building collapse under fire conditions, and describe the warning signs that may alert firefighters to a possible building collapse. So, building construction includes such things as design of a structure, the material that's used to build it, and the configuration of structural elements in the design. And what we're going to look at briefly is in each era of construction, they were all a little bit different in the material that they used and the design they used, from the colonial times up to modern day with the lightweight construction. You will see a shift from heavy timber to things that's more based off of geometry, less mass, and more cost-efficient type building materials. But each has their own problems in regards to firefighting. So let's start out with some key terms. Load, which is defined as any of the forces that a structure is calculated to oppose, including any permanent force, any moving or temporary force, wind, or earthquake forces. Architects and builders must consider structural loads and occupancy. Renovations or changes can place additional stresses on original load design. And that's one of the big problems in the fire service in terms of building construction. You may have older style homes that have been updated, and you may not be aware of said updates unless you've been in that structure, those types of structures. Or it can be the building, for example, may have started out as a let's say a retail store, and then somebody turned it into a Chinese restaurant. And the question is this retail store, former retail store, actually capable of being turned into a Chinese restaurant in terms of, is it structurally sound to support the ovens, hood vents, sprinkler systems, and things of that nature? So back to our loads. You have 2 types. You have a live load, which is any load that is not fixed or permanently attached to a structure. So a good example could be product or material in a warehouse. That would be an example of a live load on the 2nd floor. And dead loads are permanent parts of the structure, such as floor, roofs, walls. HVAC is an excellent example. Equipment, and of course elevators. Now, when we're talking about loads, you have things known as a static load and dynamic loads. Static loads are applied steadily over a gradual period, and dynamic loads are imposed by motion or something that shocks a building is a good example. So that would be like say dumping 10,000 gallons all at once on a roof, where a static load could be like rain for 2 days straight, where the water's slowly building up on a flat roof, leading to collapse. So load distribution. Uniform loads are applied over a large area. So it spreads the weight out essentially. Concentrated loads are applied to small areas of the structure. Obviously, the more you spread out the load, the less stress is going to be on the building because it's evenly distributed over all the structural membranes, as opposed to having it concentrated over just a few. When structural support elements are attacked by fire, they may become weakened or distorted. There are three categories of load impositions, and basically what they're referring to here is the forces on it. What direction are they pushing on the structural membrane? We have axial, eccentric, and torsional. Axial loads are proper loads. This type of load, the structural elements were designed to support, and it's evenly distributed. It is perpendicular to the central axis or plane. If the load imposition is axial, the supporting elements carry the maximum load capacity. So that's like a I-beam or steel girder and looking like a T. So that's our structural element there. Obviously it would be straighter than what I'm drawing. And then here is your floor or roof of the upper level that it's supporting. So that's a good example of an axial load. Here's another great picture of an axial load taken in front of a shopping center, obviously. Now we have an eccentric load, and that's an improper load. It's an imbalance, weakens the structure. Loads are not evenly distributed over the central axis or plane of the supporting structure. So this is something that's kind of off-center. Eccentric loads are perpendicular to the central axis or plane. It creates tensile stress on the side as it stretches and compressive stress on the opposite side as it contracts. So here's a good example of a column that will bend under an eccentric load. Notice how the force coming down by the arrow is off center. And then, of course, that's going to create stress on this side to stretch it out. And it's going to start kind of compressing or bending in on this side. Next, you have a torsional load or an improper load. And it is offset from the central axis, the supporting structure, but in the same plane as the cross section. This creates a twisting motion on the supporting membrane. And the good example of a torsional load is kind of like a nut going on a bolt and that twisting sensation. As seen here, the torsional load, that turning sensation like you're screwing in a screw or again twisting a nut onto a bolt. Excellent examples. Earthquake or explosions can subject a structure to both eccentric and torsional loads at the same time. The resulting stretch is dynamic, three-dimensional, and highly intense. So it's pretty much a sudden shock or a shock load to the structure. So, what are the most common loads and forces placed on a structure under fire conditions, and why should firefighters be concerned? Think about that. So let's look at some structural components now. When we think about our structural loads, everything goes from the top down, and of course gravity is always the eternal enemy of any structure. So the foundation is the final recipient of all loads on a structure. It must be stable to accept the combined comprehensive forces of the weight of the building and all the loads delivered in the building. Most are made of steel reinforced concrete slabs. So here is a formula that they use to help determine the suitability of a foundation. Pressure equals CWH divided by 2, which is times the height of the soil and the length of the wall. So, concrete is highly resistant to compression and continues to harden as it ages. Older structures may be made of wood and joist and beams, or pier and beam, as you can see a good picture in your text. These concealed spaces is the type of construction that allow hidden fire to move around and may result in floors or wall collapsing. Here's a good example of an old pier and beam foundation. It's kind of got that crawl space mentality underneath there. Beams are subjected to two forces, load and tensile force. It is important to know if a change has been made to the structure. Formulas for calculating depth, width, and span. Columns are designed to withstand compressive forces imposed perpendicular to the center axis of columns. The strength of a column is determined by the construction material, the diameter, and the length. And again, there are formulas to justify all the forces, but I'm not concerned that you guys remember those. That's another class. Walls. You have load-bearing and non-load-bearing walls. Load-bearing support the roof and the upper floors and are transmitted to the foundation in terms of weight. They function as columns. Non-load-bearing walls only support their own weight. So it's kind of like a wall that divides a room from other portions of the house, but doesn't support the roof. So you could take that wall out and the roof would not collapse. As seen here, this is a load-bearing wall. This is a good example of a non-load-bearing wall. Bracing must be added to provide resistance to lateral loads like wind and other forces for our walls. Common bracing types include diagonal bracing, chevron bracing, and X bracing. And here's just some general lateral bracing for walls as seen. Now, when we're also talking about walls, you have other known as cantilevered walls, and they are only supported on one end, and they are unable when subjected to wind while under fire conditions. Pressure exerted by wind forces can be calculated by, again, a formula, and here it is. A cantilever wall is more ornamental. It kind of just, again, sticks out from the structure and doesn't really provide any type of structural stability on the structure itself. Wood trusses and I-joists are designed by computer engineering programs. The strength of the wood truss depends on its components and connectors that tie the components and the cords together. When you're looking at your I-joist, it's made up of several different parts. And you have what's known as a top cord, a top board, a bottom cord, and a bottom board, and some interconnecting membranes that create a web. The strength of the truss is achieved by configuring the web components in a triangle. The connectors are steel plates stamped with 16, 18, or 20 gauge structural steel and zinc coated to prevent rust. Here's a good example of the gusset plates that are used to hold these trusses together. The connectors are pressed into place by a computer-operated machine. This creates a much stronger connection. The metal connectors, however, will lose its structural integrity when heated to 1000 degrees Fahrenheit. And should the connectors fail, the entire truss is likely to collapse. And that's one of the problems with our modern construction or lightweight construction. 1000 degrees at the ceiling in a structure fire can be easily obtained due to the burning of modern furnishings that are oil or petroleum based products. They burn a lot hotter and a lot quicker than traditional cotton and wood type products. So look around your house and see how much stuff is oil based or plastic based. You may be surprised. Another type truss out there is a bowstring truss, and this is used to span large open areas. And it kind of looks like a bow, as the name applies. It's arch top cord and straight bottom cord connected by a web of interlacing connections. If any components of the truss fail, tension is released and the truss will fail. So in a warehouse, if you have product burning and it's burning underneath the truss and there's no fire protection and it burns a hole in part of the truss, the entire ceiling will collapse. And that's one of the problems with this bowstring truss design, and there's some great pictures in your text. When we look at our trusses, there are all kind of enemies that go against its integrity, and that could be termites, critters, pests, you name it. The corrosion, the metal connectors, excessive dead load weight. So, the roof may have not been designed for HVAC units, but now it's got that on there. Satellite dishes, and who knows what else. Maybe the trusses have been modified some way illegally from its intended purpose. Maybe they took out a support beam that helped hold the truss up because they wanted a more open floor plan. Okay, here's a great picture of a wooden truss. Notice how we've got our triangles here and our gusset plates holding them all together. And again, the load is distributed evenly over the entire makeup of the truss system. However, if we had a fire and say that fire weakened that area right there, causing the gusset plate to fail at least 1000 degrees, then the entire roof system could collapse because its integrity comes from the whole structure and not just individual sections as one continuity structure, if that makes sense. So essentially you're only strong as its weakest length, and if one link fails, then the whole system will fail, is a great way to put it. So our I-beam / I-joists, and they're popular in the building industry now, and it allows spans up to 60 feet without columns. They're designed to take the place of the solid wood beams and wood truss joists. When you look at an I-beam, it has three parts. It has a top flange, a bottom flange, and some sort of webbing in the middle that gives it structural integrity. A wooden I-beam can support more weight than a solid beam of equal length, width, and depth. Most components are held together with glue, which in turn kind of creates a little bit of a problem because even though it's structurally sound, or even more so structurally sound than a solid piece of wood, it's highly susceptible to failure under fire conditions because that glue will loosen up, melt, or catch fire under fire conditions. Of course, the web is comprised of plywood, some sort of laminate veneer lumber, or OSB, or ornate strand board. And again, those are products that are engineered wood, meaning that they are not one continuous piece. So it's something that's held together with something else. Instead of triangles perpendicular to the I-joist, the web uses the 90-degree cross-grained wood of the OSB and LVL for its integrity. And here is a great picture than I-joists in the engineered wood. Notice how structurally sound it looks. But again, compared to the solid wood components, it does not hold up to fire conditions. However, it's sturdier and cheaper to build with than using the solid wood components. Ceiling joists, which are beams that support the ceiling loads, and they are supported by large beams, girders, or load-bearing walls. They tie the exterior and the interior walls together, and they may double as a floor joist for attics or a second story. The ceiling joist may be constructed of lightweight steel trusses, wooden trusses, I-joist, or I-beam steel, or some sort of solid dimensional lumber. And a lot of this comes to what age the house was built. The older the structure is, the more likely it was made of that solid dimensional lumber, as opposed to the newer it is, then you get that lightweight truss type design. Okay, here's a great view of an attic, and here are some ceiling joists and beams that are connected to the parallel walls that support the interior ceiling cover. So when we're looking at the roof, there are several different designs, one being the traditional flat roof, and this uses the ceiling joists as supports for the roof assembly. These, in effect, become the rafters. They tie the exterior and the exterior walls together. If the truss fails under fire conditions, both the roof and the walls can collapse. Another type of roof is your pitched roof, which most of us are pretty familiar with. That's kind of like the roof on your traditional home. But they can be conventional or prefabricated construction. The conventional are shaped and assembled on the construction side, and one rafter is built at a time, and that is called stick frame type construction. Your prefabricated trusses are assembled at a fabrication shop and lifted into place on the support structure. Again, some more great pictures of the trusses. Notice the triangle shape and the gusset plates holding them together. And this would obviously be a prefabrication type facility. So when we're looking at our trusses, here are the different components: your top cord, your bottom cord, your webbing, and the gusset plates. A pitched roof can be made of prefabricated trusses. The bottom cord of the truss is also the ceiling joist. Arched roof is another form known as a bowstring truss. Failure of the truss in a pitched roof will result in structural instability and possibly lead to collapse. Are different types of pitched roofs. You have a gable, as seen here. Here is your gable roof. You have a hip style roof, as seen here. You have a lantern style, as seen here. And to me, this kind of looks like the farm barn type. Kind of helps me remember it. You have the gambrel. And you have the shed style. And that's kind of like the whole lean-to. You have sawtooth style, as it looks like, of course, a sawtooth. You have the butterfly style. Notice it has that V shape. You have an arch. You have a mansard. And one of the problems with the mansard sometimes is this wall can be up higher than what's actually below it. So you may need another ladder to get down to the base. Now, when you're looking at the different construction types, there are a bunch of different codes that kind of help classify and decide what's to be built. The IBC, the UBC, the BOCA, SBC, and of course NFPA. Now, when we're looking at construction type as far as it's concerned in the fire service, we really reference NFPA 220 and NFPA 5000. And that references 5 different types, type 1 through 5. In type 1, and we'll go through each of these, is your fire resistant type structures, stuff that's made up of things that won't burn. So you're looking at concrete, reinforced steel, steel girders with fire insulation around them. And then your type 2 is non-combustible, and it's very similar to your type 1, except the structural membranes aren't protected from fire. So that would be like your warehouses. You know, your type 1s could be hospitals or parking decks. And then your type 3 is your ordinary construction, known as Main Street America. It's kind of like the retail type construction that you would see old-timey going down, of course, I said the Main Street, and then with, you know, the residents above. And then your type 4 is your heavy timber or your old mill style construction. Churches are an excellent example. And then your type 5 is your residential or wood frame structure. NFPA lists type 1 and 2 as non-combustible, 3, 4, or 5 is considered combustible, or sometimes limited combustible, depending on what book you want to read. Now, with that comes into play your fire resistant rating. So based on the length of time in hours that a structural component can be expected to maintain its integrity under test conditions. These ratings are based on NFPA 251 standard method testing for fire endurance building construction. So when you're looking at your type 1 and type 2 construction, they probably have things known as firewalls or fire doors, and this is what they're referring to, is how long will that structural element hold up to direct fire. And as I said earlier, your type 1 construction, your structural components are not combustible and they're protected by some sort of heat resistant material. And I'm not worried about you knowing the 2 subtypes, that's just for your information. When you're looking at type 1 443 332, that is just a more in-depth measurement. So the first digit describes the rating. The load-bearing exterior walls has 3 or 4 hours with the fire impingement. The second identifies the fire resistance rating of the interior load-bearing walls and columns, beams and girders and trusses. And the third digit identifies the fire resistant rating of the floor and roof assembly, so 2 to 3 hours, again, depending on what you like it. So this is a type 1 construction with a 4-hour, 4-hour, and 3-hour on each subcategories. Now, your type 1 construction can primarily be made up, again, as I said, concrete, but also steel. Steel is a strong structural element with the ability to withstand equal compressive and tensile forces. However, it does lose its structural integrity when it is subjected to 1,000 degrees Fahrenheit. Above 1,200 degrees, it loses all structural property and will essentially bend and collapse. But since it's type 1, that steel girders need to be insulated from the fire. And when you look at the World Trade Center, that's a good example of a type 1 construction. And notice how long it stayed upright after it was hit by the airplanes and of course the flame. Only problem is when the airplane struck the towers, the force in the explosion blew away a lot of the insulating properties that protected the steel, that prevented it from staying erect much longer to its rated potential. So the factors that affect structural failure include the mass of the steel components, the heat release and the rate of the fire, the forces that are always exerted upon it, the different types of loads, and the type of connections joining the steel components. Here's an example of some steel components and how it's bound together, which can be bolted or welded. As you see here, we have them bolted together. And here is a good example of how it is welded together. Again, I can't stress it enough. You may see it again, but steel restrained beams will distort by bending or twisting with fire conditions that reach or in excess of 1,000 degrees. Steel does have a memory and can return to its original shape after the stress is removed. So essentially, it's a little bit flexible. The point where it will not return to its original shape is the point of strain. So there's a key term for you. Unrestrained beams are dangerous. 100-foot beams can increase in length 9.5 inches when heated to 1,000 degrees. And I've seen texts say anywhere between 9 and 10 inches. But the point is, you heat it up to 1,000 degrees, it can expand and grow longer and then push out walls or whatever the case may be, which can lead to collapse. So metal will fail quickly under fire conditions, as seen here. So there's a couple different ways that you can protect the steel, and that can be plaster, lath, concrete, gypsum, or tile. And again, here's an encasement method of giving the steel that structural integrity. A second method of protecting structural steel is spraying on steel components with a fire-resistant coating, as seen here. Concrete. Plain concrete is vulnerable to tensile and shear forces. Steel reinforced concrete has steel bars or mesh added in the mix, as seen here, for added stability. So that's known as reinforced concrete. So concrete is pre-stressed concrete cast at concrete plants around steel cables. The post-tension concrete cast is placed with high-strength cables in the form prior to pouring the concrete. One important thing to note is concrete has water in it even after it hardens. So when concrete is heated up, water turns into a gas, and then as that water turns to gas in the concrete, it can cause what's known as spalling or break the concrete apart, shooting out, these little concrete shrapnel grenades, and depending on the amount of water and the structure will dictate how much is going to come out. But that can weaken the structure as well as expose internal steel components. Moving on to our Type 2 construction, which has non-combustible structural or limited combustible material. It's similar again to the Type 1 construction, but doesn't have as high fire-resistant ratings as seen here below in terms of the hour ratings for all the walls. So it has to have 2-hour, 1-hour fire-resistant rating. It's adequate construction for residential, educational, institutional, or business assemblies. Again, it has unprotected non-combustible construction and no fire-resistant rating and no structural stability in a fire for a type 2000. This is common for commercial or private properties such as business, office buildings, garages, and barns. Good example of your type 2 here. Usually they're all some sort of metal, steel, aluminum type building. So what factors should firefighters be especially concerned about when fighting fires in a type 1 or type 2 structure? So moving on to our type 3 construction, which has exterior walls requiring construction of non-combustible or limited combustible material, such as stone or brick masonry, metal, concrete, or any combination of those. Again, I said this is one of those Main Street America type buildings. Alright, type 3 construction may have legends or corbels which form between stories and support the floor joists from the next floor. Most of these buildings were built in the 19th century, and a fire these floors are designed to collapse under fire conditions to prevent the collapse of exterior walls. Meaning it kind of breaks down and in as opposed to pushing out. And here's a good picture of them. Another example of this is something that has a fire cut, which allows the end of the joist to burn faster and fall inward, as seen here, as opposed to pushing out if it was all one piece, which would cause the outer wall to go, which would lead to the entire structure collapse as opposed to just the floor. So that's the premise behind it. So some of the problems with your type 3 construction. Metal stars or plates on the exterior, and those stars and plates are designed to help reinforce the walls. So obviously the structure has been battered by time and has some structural issues that could fail during a fire. Cracks in the masonry or mortar or sand lime mortar. And sand lime mortar is one of the first types of concrete that was produced, and the reason you're worried about it is it's water soluble, meaning that it can dissolve over time, of course, with rain or with water from a fire hose. So of course once the mortar is gone, that sand and lime mortar, that concrete mixture, obviously the structure is going to lose some integrity as opposed to the modern day concrete. Here are examples of those little stars, and what they'd have is a steel bar that runs through the other side that gives the exterior wall support. Cracks. So those are all things to be mindful of. So with our type 3 construction, it has two subdivision categories. Again, I'm not too concerned that you know it. I just want you to know that type 1 is non-combustible, type 2 is limited combustible, type 3 is the Main Street America, type 4 is your heavy timber, and 5 is your residential. And then kind of have an idea of what each structure looks like. Here's a great picture of a type 3 structure. So type 4, to me this is one of my favorite type of constructions. It's heavy timber, its construction is common around the 19th century, and it has exterior load-bearing walls that were solid masonry. Or looking at our internal structures, they were big continuous pieces of lumber. So literally they would chop down trees and make your support beams. And here are all the particulars again with our Type 4 construction. Interior load-bearing walls have 1 hour fire rating. Exterior load-bearing walls have a 2 hour fire rating. And post and beam, as seen here, is a common construction method, and they were held together with wooden pins. The great thing about this type of structure is it was built to withstand fire and had a lot of its features were designed to help put the fire out. Because think about it, we're thinking about mills and such. But because the membranes of the structural components were so dense and heavy, they were resistant to fire, meaning that it took a lot of heat and a lot of time for these to lose its structural integrity. And of course, if you ever fight a fire in this type of structure and it's not knocked out initially, you're going to be looking at a very massive fire that's going to produce a lot of heat. You're going to be worried about exposures, and you're going to need a whole lot of help and water to put this thing out once it gets rolling. Finally, we have our Type 5 construction, which is your residential type stuff. Your Type 5 will have 1 hour resistant rating throughout the structure. Type 500 has nothing at all. Some of the problems with your Type 5 construction, again, this goes back to what time frame they were built. So if you look at balloon frame construction, which originated in the 1830s, it had defining features in the wall studs that ran continuously up 2 or more stories from the bottom to the roof. And these wall studs had no fire breaks or no stops in between the levels. So if you had a fire in the wall around the first floor or basement, it would run all the way up to the roof because they had these concealed spaces and voids, and would essentially burn the attic off and eventually destroy the structure. One way to identify these types of structures is looking on the outside. And since these outside supports ran the entire length of the structure, you had the windows that were the same location or parallel on the first and second floor. So here's an example of your balloon flame construction, and with that I said, you can look at, and there's a good picture in the text about the windows, how they're the same on the top and bottom. Next, you have the Type 5 construction that is known as the platform frame construction, and it became popular at the end of World War II. So wall studs only extended to the height of each floor. So basically you had a firewall or a fire gap, something to prevent the fire from spreading. So the bottom of the first floor studs were nailed to the bottom board called a sole plate that's set on the concrete foundation or wooden platform floor. The platform is constructed on floor joists covered by a subflooring, and the top of each stud is nailed to the top plate. The top plate is 2 boards nailed together to form a beam. This acts as a supporting structure for the ceiling or floor joist to rest on and as a fire stop. Okay, here's a good example of it as seen here and here. And so what it's trying to do is basically compartmentalize the fire and keep it to just that one room for as long as it can, so people have a chance to escape a burning house, and hopefully firefighters have a chance to get there and extinguish the fire. So there's a lot more to building construction. Again, we're just offering you a brief glimpse of several key terms and some different types of construction methods. Once you take building construction, you'll see more of the structural elements as well as the different subcategories for each, and how fighting fire in each one of those structures can be a challenge. So let's summarize this text. Buildings are designed to carry specific loads and endure specific forces. A building consists of a foundation, floor, walls, and a roof. Walls, columns, and foundations are designed to resist compression forces. Beams and girders are designed to resist tensile and shear forces. NFPA 220 and NFPA 5000 building code list 5 types of building construction. Remember, our type 1 through 5. Type 1 is our non-combustible. Type 2 is our limited combustible. Type 3 is your retail. Type 4 is your heavy timber, mill style. And type 5 is your residential structure. Firefighters should be familiar with the many different types of construction in their area and the possible dangers involving in each of those buildings. So, we covered a lot. Make sure you do your review questions and, of course, read the text if you haven't already. You can email me at aroberts@athenstech.edu or give me a call in the office. Until next time, be safe and have a good day.